Good afternoon, everyone, and welcome to the session, Digital Transformation and AI for Climate Security. I'm Sumaya Sejudi from UC Berkeley, and I have the honor of chairing this session. I'm delighted to introduce our first speaker, Professor Nuyara Hovakamian. Nuyara is a professor of mechanical science and engineering at UIUC, and she will talk about intelligent agricultural management for soil carbon sequestration via reinforcement learning and large-scale simulations.
Thank you for the honor to present in this event. So to get started, I'll introduce my UIUC co-PI, Nico Martin, and the postdoc Pan Zhao, and students Rantao and Jingwu, who helped us to get the results in this presentation. This is actually a bigger project, and we have KTH collaborators as well. Professor Zara Kalantari from KTH with her postdoc, Carla Ferreira. And Guillermo Marcillo was a postdoc of Nico Martin. He got a position and left us last year. So here are also our students. Thank you for the opportunity to work on this research. So as we all know very well, so global warming is not a prediction, it's really happening. In fact, I remember that as a child, my mom used to talk a lot about global warming. She's a PhD in geography, presenting it as one of the biggest threats for our planet Earth. Today, we have to come up with real solutions that can help us to fight this climate change. So one of the opportunities is to do it through carbon sequestration. So it's clear that the global soil carbon pool of 2,500 gigatons is 3.3 times larger than the size of the atmospheric pool. Soil carbon sequestration has the potential to offset 5 to 15% of the global fossil fuel emissions. Cropland soil has the highest soil carbon sequestration potential among all types of soils. It's known that 157 million hectares of US cropland have the capacity to sequester up to 100 teragrams of carbon per year. Conversion of natural to agricultural ecosystems causes depletion of the soil organic carbon by as much as 70% on average. So an increase of 1 ton of soil carbon pool of degraded cropland soils may increase soil crop yield by 20 to 40 kilograms per hectare for wheat, 10 to 20 kilogram hectare for maize, and up to 1 kilogram hectare for cow crops. So moving forward, so there are many agricultural management practices that influence the soil stored carbon. There's like conservation, tillage, cover crops, fertilization, mixed farming, irrigation. So these are decisions that the farmers take throughout the year. And it is challenging to find the optimal management practices, maximizing soil carbon sequestration while improving the crop productivity. So we are all very well familiar, I'm sure, with precision medicine because we go and see our doctors twice a year and so on. Digital agriculture is a relatively junior industry in this sense. So lots of the things that are happening today in this industry are happening based on practices, common sense, farmers' experience, and others. So now it's the time to revolutionize this industry as well, with the opportunity of data collection through so many sensors, aerial imagery, with the satellite data resolution becoming higher and better. One can truly optimize these practices to get better performance for crop yields and to optimize the management, as well achieve the carbon sequestration. So this agricultural management is a sequential decision-making process, as I said, irrigation, fertilization, and so on. So it can be modeled by Markov decision process. And reinforcement learning methods can be leveraged to optimize these processes. And we know some of the well-known success stories of reinforcement learning in computer games, in robotic industry, and many others. So the vision is that we can try to bring these methods to agriculture to see how to improve these practices. To do so, we need some simulators where we can train the management policy. And while we train the management policy, we can basically implement it in real world by using the sensors for real-time measurements. To close the real to sim gap, we need some type of experiments, and I'll go ahead and talk a little bit more about it. So training management policy using deep reinforcement learning may need millions of interactions between the reinforcement learning agent and the cropping system, infeasible for field experiments. So we let the agent interact with the cropping system simulated by AppSim and DSAT. These are the two most recognized crop simulators. So in this particular case, in this paper, and by the way, the paper will be presented in the upcoming CVPR conference. There is a special workshop on remote sensing where the paper will be presented. So this set is a type of simulator that's initially used for algorithm validation, as existing development allows for it to be directly used for RL training. So it has the APIs. We can train an RL algorithm, reinforcement learning algorithm. While AppSim, which is equally popular, if not more popular, will be used for validating the effectiveness of the proposed framework on Illinois and central Portugal farm fields. To implement the Markov decision process, train an RL algorithm, we need to understand what are the states and what are the actions in this particular context. In the context of agricultural management, the states are the crop status that can be measured by height, leaf size, and so on, weather condition, soil condition. And the actions will be fertilization, irrigation, residual retention, and cover crops, for example, that are quite popular, tillage, and so on. So we have to select a reward function, and this is already us designing the reinforcement learning algorithm. The reward function will be a weighted average of stored carbon yield, nitrogen leach. In this particular case, we are doing nitrogen management, and the management cost, that's the cost of the fertilizer. So the W1 to W4 are the weights. So here is how the process works, right? So we have the environment, so that's in the simulator. We collect the tuples. S would be the state, A would be the action, R would be the reward, the one that we designed, S prime would be the next action, like thinking of Markov decision process. We collect them in replay buffer, we do the optimization, find the weights, and implement the policy. So this is the particular loss function. For DeepQ network, we also trained a soft actor critic in this paper. And we do domain randomization by randomizing weather conditions during the training, so that to improve the robustness of the trained policies against uncertain weather conditions. Here are some preliminary results for nitrogen management. Nitrogen management is recognized like one of the most important actions throughout the season of the crop's life. So this is the reward function that we implemented. The weights, we choose discrete action space. These are very preliminary results because we got the funding sometime in fall till we studied and picked up the simulators with all their tools, how they work, how to implement. So we pick 5 possible actions per day in terms of nitrogen fertilization. We set the irrigation to 0. And as I said, we implemented for a database of Iowa and Florida. For Florida, it would correspond to a severe drought condition. In reality, the irrigation should not be 0, but for simulation purposes, we could test the extreme conditions. We pick 35 states output by the simulator offered. We can pick more states. It includes soil conditions, plant growth stage, weather, and date. And we train the, for example, DeepQ network here. So the policy converges within 1,300 episodes, and here is a zoomed-in version to see what's happening in this process. The weather conditions were used from 1999. So we compare it to some baseline approaches available in the literature, which are based, as I said, on farmers' common practice, on adopted techniques that they have used. And we see that the trained policy, for example, leads to more yield and roughly the same leaching with the same amount of fertilizers, right? So the numbers are highlighted in yellow. So the trained policy will give us 290 kilogram per hectare uptake of the nitrogen for the yield of 10,855 kilogram per hectare. The cumulative reward, this is the number that comes up from that cost function. The baseline policies here indicate two other cases when the input was the same in the first case, in the second case, slightly higher. And we see that in all the cases, our optimization yields better results. From an economic perspective, right, so you don't want the farmer to go into the farm every day and to apply fertilizer. So actions can be taken instead of every day, every 7 days or every 10 days. And the optimization will reveal, for example, that so if you're applying every 7 days or 10 days for the same yield, we get more uptake, for example, and higher cumulative reward and higher yield, as we see. For the Florida case, so we took the weather conditions from 1982. The policy converges within 1,200 episodes. And final cumulative reward per episode reaches 600. And we compare it again to the two baselines available from the literature. And as I said, setting irrigation to 0 corresponds to severe drought conditions, and applying fertilizers following the trained policy yields to better cumulative reward, more yield and less leaching with fewer fertilizers. Again, we change the frequency of the action, and we can compare and see that by changing the frequency of the action, the cumulative reward is slightly smaller than that of acting every day. However, it is still larger than the baseline approach. So in summary, we present a framework, and this is maybe the first time such a framework is presented for this particular class of problems, where we leverage reinforcement learning methods for Markov decision processes to find an optimal solution for taking this sequential decision-making for farming practices. And the results are obtained for Florida and Iowa, but we can leverage the other simulator, which is better tuned for Midwestern states, Illinois, for example, to validate these results. However, we haven't yet done that. So the next steps would be to develop a crop simulation environment for reinforcement learning training based on AppSim, which has been better calibrated for the US Corn Belt regions. Train and evaluate management policies for soil carbon sequestration using the AppSim-based simulation environment. And evaluate and improve the performance of trained policies under partial observability when some states are not available, for example, the daily leaching. As with all optimization problems the way we do, so we can tune the parameters, we can tune the frequency with which we interact with the crop and so on, and submit subsequent proposals. With that, I want to thank you again one more time for the funding, and if there are any questions or if I have time, I'm happy to take a question or two. Okay.
Hi.
Hi, Carl.
Did the reward function include anything about the costs of the farm equipment, like the gasoline?
No, not the equipment. We just put the fertilizer cost for now.
Yeah,
But it depends upon the simulator. We can most likely develop the simulator to include this cost as well. But I'm not sure if at this point the simulator includes the equipment cost or not. I don't know, maybe Pan knows. Pan, is the equipment cost in the simulator? My postdoc is here.
It's a little bit of a worry that could overwhelm the other.
No, I agree, right? So it's one of the things that if it's not in the simulator, it should be added most likely. Okay.
Is there any dependence on the, the change, climate is changing, and how to what extent this non-stationarity that we are seeing affects your results, simulator and other results?
Climate change, you mean?
Yes.
Weather conditions, you mean?
But, no, I mean that the statistical characteristics of the weather now are changing in a very definitive way.
Right, sure. It's all about developing the simulator to address these issues. And the simulator developments have big teams. I think these issues are being worked out as a part of the simulator development. The future of this work is how one develops the simulator, how one develops the RL algorithm, because we find how much development is needed there in terms of new developments, new ideas, to make them more suitable for this context, these tasks. So overall, like, part of the future development of this research involves simulator developments to address the issues you say, RL developments to target them to this class of problems, learning more about farming and crops, different crops. I mean, that's a good question. So, but it's part of the simulator development.
So the simulator will take some time because it will take a lot of data to stabilize on something that works. In the meantime, we are facing all these changes. So I guess it will be in a transition state then. In the meantime.
Right, right. Mm-hmm. Oh, okay.
Naira, how and or why did you choose the sites and the particular year for your data set?
How did I choose what?
The sites, Iowa and Florida, and also the date was, I think, 1982. What?
The weather condition, because the baselines were available and these data were easy to apply to this set simulator. AppSim is better calibrated for Illinois, but AppSim does not have the APIs to run reinforcement learning algorithm directly and straightforwardly. As a simulator, it needs more development. This set had the right environment to apply the algorithm quickly. So there is some computer science work also to be done. You know, this is the first result we're first coming up, and there are so many things we're finding out that we thought we would do it this way. The simulator is not ready. We thought we would use this. So this was the quickest way of coming up some results for this event and for the paper we submitted. Right, so, and we have a CVPR paper already submitted. So this how much, it's new, this is all fresh from the oven, very new. So as a research and development, right? We haven't seen other papers even to compare, and so we use some baselines. But hopefully it takes off from here. More questions?
All right. Thank you. So this time, can you speak again? Thank you.